Hi, I'm Barnaby. I'm the team lead for StratSets, and this is our critical design review for the Mach-25 competition. I'll pass straight over to the mechanical team to give a brief launch vehicle overview.
I will now take you through an overview of the launch vehicle. Here you can see a full section view of the CAD. You can see we've got larger fins. The motor mount tube has now got a retaining ring attached on the end. Due to feedback from the RSOs, we've also now got an aft recovery bulkhead which contains a U-bolt for attaching recovery systems. The flyaway rail guides are modelled right here. Avionics and CANSAT have got updated models, as well as now an ejection piston and an advanced model of the nose cone.
The vehicle nose cone is primarily a fiberglass layup, also including PLA and phenolic components, which are attached together using M3 screws and epoxy. The fiberglass layup itself is created using a PLA mold. It's a concave mold, which the fiberglass is laid up on the inside of, and then there's a second convex component which inserts in and is clamped together in order to get a good finish on both sides of the shell. The nose cone separates into two components, so we can access the internals to tighten the fixtures and to add ballast if it's required. We haven't made a final decision on this yet. That will be made once we have weighed all of the components. The nose cone connects to the shot cord using an eye-bolt at the base, and from our feedback in the preliminary design review, we have extended the surface to which the bulkhead epoxies to in order to provide a stronger mate.
For the CDR, we had these requirements done. However, we're still missing a few of them. We printed a test print of the avionics bay to help decide the changes that need doing. Here it is. It was printed with a very low infill, so it's not representative of the actual strength. The avionics bay has been a bit restructured. Although most of the modules remain the same, the camera has been moved from the side with the backup tracker, and the RBS have been moved to the side with the batteries. The short-range tracker drawer has also been moved to the side. This allows for just more space and more wiggle room with our flight computers to make sure we have enough tolerances in there. Our hinge has been added to the camera faceplate, the camera faceplate, and the compliant mechanisms have been tested on the test print. We decided that these weren't quite secure enough, and so we are going to put bolt points and mounting points just so as a final bolt can be added before flight to make sure that the plates do not open during it. Wire channels have been added for the RBF board and for the pyro wires up at the top. LED mounting points have also been added in the field of view of the camera. Those can be seen here. Decorative features also double as wire channels should we run out or the ones that we have are not appropriate. Colored string has been used to demonstrate the wiring on the avionics bay. The wire channels on the side of the batteries fit the wires which will be used. This was tested the other day, however there are no wires in it currently. There. Mounting points have been checked with COTS flight computers and with Firefly Ultra to ensure that everything fits together. Firefly Ultra is the computer that we're hoping to certify. It doesn't control any pyro, however it will control the LEDs at the front of the faceplate. There's been space added for removal tabs for the batteries. Those can be seen on our test print here. Those work, however they've been slightly changed due to the walls not being thick enough for 3D printing. We have also added space for our hardware to go through on the top of the avionics bay. Space for threaded inserts to fit into the side of the avionics bay have been added. Those will go there and they will attach the parachute bay to the avionics bay on either side. As well as all of the threaded insert holes we did a test print to figure out how much tolerance those needed around where the threaded inserts were to find just how strong they needed to be and what size they were. So they've all been updated to be the appropriate size for printing. The mounting points have been added for the through terminal blocks. Those are on either side here and here. And due to the nature of these, our bulkheads have had to be changed. The bulkheads will now be made up of two layers. The top layer being a fiberglass sheet, 3mm fiberglass, and the bottom layer being a 3D printed flat plate. This 3D printed plate will have a couple notches in it. This first one allows for it to match with the coupler tube, which will have a bit cut out of it, meaning that the bulkhead can only attach on one direction. This hole here matches with the top of the avionics bay, and that also allows for the sled to only go in one single allowable orientation. There's matching versions on the other side. It is mirrored, so it cannot be, the bulkheads can't be put on the upside down either. Overall, it's still all together, held together with threaded rods, which go all the way through. Those can be seen at the top. And the camera hole, which can be seen here, will double as an ingress point for our ejection test. We've decided not to use an O-ring or sealant, as I don't think it's actually necessary. The hole that is created from the through terminal block should be exactly the same type of hole as the hole that is needed for the ejection wells. However, correct me if I'm wrong on this, there is still space and room that we could add an O-ring or a form of sealant if necessary. There's, so with that, we've completed these requirements, and that is all the requirements that we had necessary for the AV bay up until this point. With that, we have our final design. This just gives an overview of what it looks like. This diagram here shows where it will be sliced directly along the center. This is how we sliced this one. It reduces the amount of supports needed for it and has been very good. It will be glued together with super glue, which we have found to be plenty strong enough. This was only with a little bit of super glue, so we're not too worried about connecting it back together. Other than that, here's drawings of our drawers and fake camera faceplate. Here are the tubes, and here are the bulkheads with little isometric assemblies. Here's the exploded isometric. Don't look too closely. It's fine. So that is our avionics bay. Now passing over to the FARGs.
The flyway rail guides will be constructed by carbon fibre rods, which will be purchased and then cut to size and placed in centering rings created from 3D print filament, which will feature holes in the top to allow for epoxy resin to be filled in, keeping the carbon fibre rods in place. There will be springs placed around the rim of the centering rings in order to keep the flyway rail guides closed until sufficient force produced by the rocket upon launch will separate them and allow the flyway rail guides to separate. A change from our initial concept was that the carbon fibre rods have now been reduced from a 10mm diameter to a 5mm diameter in order to save on weight and save costs, as the additional strength provided by the increased diameter is not necessary for the load applied to the flyway rail guide.
I will now take you through our fins, bulkheads and centerings. These will all be water jet cut out of 3mm GFRP sheet. The fins have been made larger due to feedback from the RSOs at PDR, as well as due to changes in a mass budget. The fins will be attached via fin tabs inside, as well as they will have fillets on the outside of the rocket to make sure that they are secured, as well as having internal fillets. The airframe will be made out of fiberglass tubes bought from Giant Leap Rocketry. We chose Giant Leap Rocketry because they are compatible with the Black Cat Rocketry airframes, as well Black Cat Rocketry couplers, as well as having been mentioned on Black Cat Rocketry's website as an element of trust. They will be 98mm diameter with an approximate outer diameter of 102mm. The open rocket density estimation has been used for the fiberglass until we've got the tubes and we can weigh them ourselves. And the Black Cat Rocketry masses have been used for phenolic in where it is applicable. Here you can see our preliminary mass budget. This contains margins for components that we do not have and will be updated as components arrive.
So here we have a diagram of our open rocket model. Since the preliminary design review, we've enlarged the fin slightly to account for corrected mass and in response to the RSO feedback. In addition, we've finalized the airframe and coupler lengths, and the parachute sizes have been increased. The reason we've increased the size of the parachute is to decrease the landing speed that little bit more in order to increase our chances of no damage on recovery. In terms of drift, in the worst case scenario at 15 meters per second wind speeds, we've managed to limit the range to 330 meters at a 10-degree angle. In addition, the larger parachute means we're touching down at a speed of 7 meters per second. We're currently predicted an apogee of 1,950 meters with a maximum velocity of 263 meters per second and a maximum acceleration of about 19 Gs. Here we have a graph of our static margin. At the moment it's between 1.6 and 2.6. This is very slightly above the upper range set out in the guidelines, however it's not that much of a concern for safety. Simulations suggest that no ballast mass is required in order to fit in this range. However, the real masses will be used in OpenRocket and ballast will be selected as appropriate. In terms of our motor selection and procurement, we're still intending on using the K1440 that we were intending to use last year. At the moment, this is currently in the possession of John Bonsor and will be taken to the launch site at the appropriate time.
For our recovery, we have a Easy Mini as our primary recovery, and we have an Egg Timer Quark as our secondary. This is a dual redundant setup, and they will both be tested in a vacuum chamber with the same altitude settings as last year.
The Ultra Ground Station will allow us to communicate with both the rocket and the payload, transmitting commands and receiving important telemetry data which will be processed and displayed on the onboard screen. Additionally, we will use a tracking ground station for use with our live video streaming payload board as seen in the diagram on the right. It can be seen from the power budget shown on screen now that our worst case power consumption for the ground station is 386 milliwatts, which is relatively low and is why we can power the entire board with only one lithium-ion cell. This is the current PCB layout for the Ultra Ground Station. As you can see, there are 4 SMA connectors for radio antennas and 4 LLCC68 lower transceiver chips on the left. 2 of those will be used for the rocket and payload respectively, with the other 2 optional for future expansion. There, as you can see, there is a holder for a single lithium-ion battery to power the whole board, as well as a small CMOS battery. There is a microcontroller in the top center next to a GPS chip which will be used for accurate time tracking. Additionally, there is an ST-Link connector on the side for programming and debugging and a USB-C connector for power and data transmission.
The ground station will be able to read telemetry data from the rocket and display it on an onboard display. The onboard microcontroller will be able to process and display the requested stats, such as maximum height or maximum velocity. There are 4 radios allowing for communication with up to 4 Firefly Ultras over frequency division multiplexing, with the opportunity for even more using time division multiplexing. The operating frequency is 868 megahertz in the ISM band, and the power is within the IR 2030 1-14 bands, like rules. And there's a GPS on board to provide accurate timing for time division multiplexing.
There's been significant progress on the ground station board since the Mach-25 PDR. Most notably, we now have all components on the PCB, including the main battery holder, GPS battery holder, and various other connectors. The ground station requirements have now all been met compared to just one GS-006 being met in the PDR. Video streaming, we'll be using a 2.4 GHz frequency rather than the 869 MHz frequency used for telemetry. This requires a more directional antenna and therefore greater pointing accuracy, which we will provide using our tracking ground station. The tracking ground station will use NEMA 17 stepper motors to ensure accurate positioning and pointing. We will determine the position and where the tracking ground station needs to move to based on telemetry received by our Firefly Ultra from the payload. The Firefly Ultra will then control the motor driver to ensure accurate pointing. The video stream will be received and processed by a Raspberry Pi, which will be connected to the Firefly Ultra for data transmission and power transfer. The tracking ground station will include mounts for 2 Yagi antennas, providing an option of a second antenna on the tracking ground station. All boards will be powered by car batteries to ensure they have sufficient power over a longer period of time, as they are quite power intensive boards. A 5 GHz Wi-Fi hotspot signal will allow the live video feed to be shown on a laptop.
I will now take you through an overview of the payload of the vehicle. The computer side of the CANSAT, as well as the shell, will be printed out of PLA. There will be 2 threaded rods running the length, M6 threaded rods running the lengths of the CANSAT, providing the majority of the strength, as well as 2 U-bolts on either end for recovery hardpoints attached to to 3mm fiberglass sheets bulkheads. The outer diameter of the CANSAT is significantly smaller than the inner diameter of the airframe tubes. This is to ensure that the CANSAT can move freely within the tubes during ejection. The CANSAT will also be ejected using an ejection piston, once again to ensure movement. The CANSAT has 2 hinged doors to allow easy access to the computers contained inside. These doors will be secured with bolts during flight to ensure that they do not open. The computers inside will be mounted with threaded inserts, bolts, and TPU washers. On the bottom of the CANSAT, there is also a camera facing towards the ground, mounted in the center, so that any effects from rotation during descent are minimized. Contained within the CANSAT, there are 2 SRAD computers, Firefly Ultra and our streaming board, mounted here and here, as well as 2 COTS computers, an RGCam global shutter camera mounted on the bottom, and Pi Compute Module 5 mounted on top of our streaming board, as well as 2 independent trackers. The Sinotrack 2G tracker mounted here, and a Find My Device short-range tracker mounted in the end of the CANSAT. The 2 independent trackers have their own long-life power supply, so can be mounted and left alone without needing to worry about power. The rest of the computers are powered off 5 RS Pro 18650 batteries. Here's an annotated diagram of the CANSAT. Notably, the attachment points for securing the doors during flight have yet to be added. They will be added very soon. The descent of the CANSAT will be controlled using an 18-inch parachute. Simulations we have used, this estimates a 13.6 meters per second descent rate. This will be deployed at apogee using the ejection piston. When stowed, on top of the ejection piston will be the drogue chute, followed by the CANSAT, and then the CANSAT parachute on top of the CANSAT itself. The shroud lines will be very likely attached to the side of the CANSAT using some de-sticked tape to ensure that they do not tangle with the main chute. The camera in the CANSAT will be pointing out a hole in the side of the rocket to capture video of ascent. When it is deployed, the 2 off-center U-bolts on the ends of the CANSAT will make sure that the camera is pointing downwards, and the shroud lines will attach to both ends of the CANSAT. Here is an annotated diagram of our ejection piston. The ejection piston is 100 millimeters long, which is just over the inner diameter of our airframe tubes. The outer diameter is 98 millimeters. This diameter will be controlled as it will be a hand fiberglass layup and will lay up on the inside of a mold. It is estimated to be roughly 3 millimeters thick. Once the part has been manufactured, dimensions will be updated.
This is our SRAD flight computer, Firefly Ultra. It includes a high-range, low-precision 3-degree of freedom accelerometer, a low-range, high-precision 6-degree of freedom IMU, a 3-degree of freedom magnetometer on the front side. On the back side, we have a pressure sensor for apogee detection, a GPS module for the recovery, and we aim to use sensor fusion to combine all of this data to get an accurate reading of where we are and where we're going. In terms of development for the PCB, the PCB shape has been finalized, all of the components have been finalized, the antennas have been chose, all of the component placement on the board itself has been finalized, schematics have been finalized, all that's left is a little bit of the final writing and should be finished development and ready to be manufactured soon. The current plan for sensor fusion is to use an unscented Kalman filter. We will collaborate with experts in the university to develop this algorithm for all available flight data. Full development of this is not required for the Mach launch. Here are all the batteries we used throughout all of the projects. We have the RS Pro 18650 and the RS Pro 12-volt T1. Here we detail the power system for our avionics control. We have 2 18650 batteries for the Quark Egg Timer. We have a shared 18650 for Firefly Ultra and our Easy Mini. And we have our RBF switching board to switch power to each, but this can be interchanged for the screw switches if needed. We also have pluggable terminal blocks for connection through the bulkheads. Based off of these photo interrupters and a key, the key has to be removed for it to be turned on. We have tested these based on the worst case scenario, as it is a relatively new technology for us. However, we've made it its own standalone module, so if worst comes to worst, we can just swap it out for a board with screw switches.
The removable flight pins can be inserted through the airframe and the coupler, and they reach into a sort of cavity where there is a spring in the pin which springs into place, locking the pin in. It has rounded corners, so the pin can be removed fairly easily, but We found that when we test printed them, we needed to unround them slightly. And the enclosure for the roof for flights themselves is fairly dark, so it is more effective with the laser. These can be swapped out for screw switches should they be found to not be appropriate.
This is the power budget for Firefly Ultra. In an average worst case scenario, it will draw 630 milliwatts in flight and 306 milliwatts during recovery, with an average lifetime of 20 hours. This is a brief power budget for the streaming board. It has 3 radios and a Pi Compute Module M5. In the average worst case scenario, it's going to draw 30 watts with a lifetime of 1.3 hours. This is the payload, the streaming board. So the power is going to be 2 S2P 1865 RS Pro batteries. It's going to then go into a buck regulator, which is going to convert it down to 5 volts, 5 volts 4 amps for the Pi Compute Module 5. We're using an AudioCam global shutter for the camera to take the video. It'll then be connected through a JST connector instead of a ribbon connector to the Pi Compute Module, as last year we had issues with that connector. The Pi Compute Module will transmit through radios, and I'll do this through multiple radios, which will increase throughput and allow better communication. And then we have a USB connector, which is going to be useful for debugging.
The Raspberry Pi 5 compute module is chosen as our hardware platform. We've begun preliminary testing of this hardware. For our land use, we've started development of software to use pre-trained models to build this land use identification program. We're looking into using UNet for the architecture. Testing will be done using still images taken from a similar altitude and resolution. And for our compression, we've explored different models for video compression, and in order to choose the most suitable one, this will be tested at different bit rates to identify our optimal balance of quality and bit rate. With our current model, we're able to get up to 0.02 bits per pixel. Quality of video compression will be evaluated using the industry standard methods such as SSIM, VMAF, and PSNR to compare the uncompressed stream to the compressed stream. We will also evaluate the AI compression against standard compression algorithms such as H.264, HEVC, and MP4, with possibility of tailoring our own model for the use case, but this would require training our own model.
I will now take you through the testing of the vehicle. In terms of airframe testing, the airframe has been ordered and should be arriving from in the next few weeks. As a result, we've not been able to do any extensive testing on the airframe itself. In terms of our recovery testing, the main chute will be the same one as we used on Stratosphere 2. This has proven itself in flight to be capable, but we will make sure that it has not been damaged over time in storage or during flight. We will be doing injection tests at Fairley Moor as soon as possible. However, it is closed for lambing season until late May. In the meantime, we will do some ground tests without using black powder, so we can do them as soon as we are ready. This will just involve pulling the shock cord and making sure that everything can move with it freely within the vehicle. In terms of payload testing, the CANSAT is now in a state where it can be test printed to ensure that all tolerances and fittings are good. The avionics bay has been test printed. Wiring has been checked. Fit checks of all the computers have been completed, and any adjustments that have been needed have been noted and implemented in design and is ready for a second prototype. Additionally, in both the CANSAT and the avionics bay, the computers will be mounted using threaded inserts. To make sure that we have got the correct size for the threaded inserts, we printed a board with various diameter holes and tested which ones they fit in best.
Firefly Ultra will undergo a series of tests to ensure critical operational requirements are met and validate performance of the key subsystems. Test plans for the key subsystems can be seen to the right. There's the power one and there's the sensor one. The PCB smasher will be used to test the stability and stiffness of Firefly Ultra. Some preliminary tests have already been carried out. The individual sensor function and testing will be carried out by the coding team. A vacuum chamber has been used to test the barometer to ensure it reads correctly. In terms of testing for Firefly Ultra, we have tested and confirmed that the low-range, high-precision IMU is functional. The GPS has been tested by standing outside and confirming an accurate fix from a cold start. For the electronic streaming board, we have testing plans to be created. We need to do the power draw, the overcurrent safety, and the radio tests. We've already tested the radio once, but we'll be testing with a spectrum analyzer in the next few weeks to get an idea of the performance and if it's to overheat. In terms of our components off the shelves, we have the vacuum chamber tests for the barometric components, and we have our ejection test to simulate our deployment at apogee.
I will now take you through the safety of the vehicle. Here you can see our risk assessment matrix. Since there have been no significant changes since our preliminary design review, there have been some minor updates, but generally speaking, no major changes in the risk assessment table.
Here are a list of guidelines for the Mach-25 competition. Here's our mission requirements and our motor mounting requirements. Here's the stability margin and our structural acceptance requirements. Here's our recovery requirements and the alternative recovery requirements and the battery bay requirements. Here's our AV bay requirements and some of our open rocket requirements.
Now moving on to the project planning section. A breakdown of our budget is as follows. Our overall budget for the project, excluding the entry fees, is £2,470.39. A diagram of this budget breakdown is shown in this tree map. A detailed breakdown of this budget breakdown will be shown in Appendix B. In terms of where the money is coming from, £3,500 of our budget has come from the University of Strathclyde Alumni Fund, as well as £1,000 towards the entry fees from the Strath Union Executive Fund. And finally, the RS Student Fund contributed £500 worth of products towards it, of which £200 of this was used towards this competition. This slide shows a breakdown of our timeline. And now to conclude, since the preliminary design review, we've redesigned the avionics bay, some of the prototypes have been produced, our RGCam for the cams has arrived, and the Firefly Ultra development board has been assembled and testing has commenced. In terms of unfinished work, our mechanical manufacture is yet to begin. We've got quite a few parts waiting on arrival, and our mechanism for the tracking ground station is still in need of design. Finally, I'd like to thank our sponsors, Altium, JLC PCB, RS Components, ANSYS, SolidWorks, the Strathclyde Union, as well as the Strathclyde University Alumni Fund. Thank you very much for your assistance, and thank you for listening.